Section 1 Introduction. We're here to talk about a development that's taken place in the realm of large language models, also known as LLMs. Over the past few years, these LLMs have been making impressive strides in natural language understanding. They've shown great promise in understanding semantics, providing answers to questions, and generating text, especially when they have few or no examples to guide them. Now, let's move on to how these models have been used for tasks that involve images. As depicted in Figure A1, approach involves using a vision encoder that's been trained to transform each image into a sequence of continuous embeddings. This transformation allows the LLM to understand the image. In another method, a vision encoder that's been trained in a contrasting manner is kept as is, and new layers are added into the frozen LLM. These new layers are then trained from scratch. There's also an alternative method which suggests that both a frozen vision encoder and a frozen LLM could be used. This combination is made possible by training a lightweight transformer. However, while these research directions have shown progress, they've also highlighted a significant challenge. The computational resources required for these additional pre-training stages can be considerable. Moreover, there's a need for large datasets containing images or videos and text for aligning visual and language modalities on top of an existing LLM. For instance, consider the Flamingo model. It introduces new cross-attention layers into an LLM to incorporate visual features, which are then trained from scratch. Despite using a pre-trained image encoder and a pre-trained frozen LLM, the multimodal pre-training stage still requires a whopping 2 billion image text pairs and 43 million web pages. This process can take approximately 15 days. But there's another way, as illustrated in Figure B. This method involves extracting information from visual inputs and creating detailed textual descriptions, such as tags, attributes, actions, relationships, and more. This information is then fed directly into the LLM, avoiding the need for extra multimodal pre-training. This leads us to the introduction of LENS, an acronym for Large Language Models Enhanced to See. This approach uses an LLM as the reasoning module and works with independent vision modules. In the LENS method, we first extract rich textual information using pre-trained vision modules like contrastive models and image captioning models. This text is then fed into the LLM, allowing it to perform tasks like object recognition and visual and language (VNL) tasks. LENS eliminates the need for additional multimodal pre-training stages or data, thereby bridging the gap between the modalities without any extra cost. By incorporating LENS, we end up with a model that works across various domains right off the bat, without any additional cross-domain pre-training. Plus, this integration allows us to take advantage of the latest advancements in both computer vision and natural language processing, maximizing the benefits we derive from these fields. In summary, our contributions include the proposal of LENS, a modular approach that addresses computer vision tasks by utilizing the few-shot, in-context learning capabilities of language models through natural language descriptions of visual inputs. LENS allows any ready-made LLM to have visual capabilities without requiring additional training or data. We use frozen LLMs to handle object recognition and visual reasoning tasks without the need for additional vision and language alignment or multimodal data. Our experimental results show that our approach achieves zero-shot performance that competes with or surpasses end-to-end jointly pre-trained models like Cosmos and Flamingo. Section Summary. Large language models, LLMs, have shown remarkable capabilities in natural language understanding, but integrating them with computer vision tasks has been challenging due to the computational expense and the need for large datasets. To address this, we propose LENS, a modular approach that leverages pre-trained vision modules to extract textual information from visual inputs, which is then fed into the LLM for object recognition and vision and language tasks. LENS eliminates the need for multimodal pre-training and enables off-the-shelf LLMs to have visual capabilities, achieving competitive zero-shot performance. Section 2 Related Work. Section 2 Related Studies 2.1 Large Language Model Abilities. Large language models, LLMs, have showcased impressive capabilities in understanding and reasoning in natural language. An instance of this is GPT-3, capable of tackling intricate tasks like translation, inference, and reasoning based on common sense in settings requiring no prior examples or just a few. GPT 3.5 and GPT-4, the recent advanced versions, are capable of interacting and generating responses that resemble human interaction. They are noted for their ability to execute an array of tasks with a few examples. Recent endeavors are also focusing on creating open-source LLMs, like Bloom, Opt, Llama, and Flant 5, that are competitive with GPT-3. However, none of these models can directly deal with tasks necessitating reasoning from a visual input. In our study, we utilize these LLMs as static language models and equip them with textual information from vision modules, allowing them to perform object recognition and vision and language (VNL) tasks. 2.2 Contrastive models for vision and language tasks. Foundation models have exhibited the capacity to identify any visual concept using an external vocabulary, irrespective of the constraints of classes or labels present in supervised models. However, past studies have indicated that these contrastive models cannot directly solve tasks in zero or few shot settings. To rectify this, a method was suggested using CLIP for visual question answering (VQA) tasks by transforming questions into a mask template that CLIP can respond to. Nevertheless, their approach needed fine-tuning to expand the model's abilities for tasks such as visual entailment. In our study, we suggest utilizing the capabilities of contrastive models and merge them with a crowdsourced open-source vocabulary to tag and assign attributes present in the image. This, in combination with a static LLM, can solve various VNL tasks. 2.3.1 Image captioning. The domain of image captioning has experienced substantial growth in recent years. The goal is to generate natural language descriptions for images. Many deep learning models have been proposed to meet this end. Remarkable recent models include Blip and Blip2, which exhibit stellar performance on NoCaps and COCO datasets. At the same time, ChatGPT has been used alongside Blip2 to create richer visual descriptions. Other studies like Socratic models and visual clues use textual data to bridge the gap between vision language models and language models. Specifically, visual clues constructs a semantic representation of an image using structured textual prompts including image tags, object attributes, locations, and captions, leveraging the GPT-3 LLM to generate image captions. Our work draws inspiration from visual clues. However, rather than generating captions, we aim to use the raw, meaningful vision data with a static LLM to solve vision tasks. Section Summary. Large language models, LLMs, like GPT-3 have shown impressive abilities in natural language understanding and reasoning, but they cannot directly solve tasks that require visual input. Previous work has attempted to address this by combining contrastive models with LLMs, but their approaches required fine-tuning or converting questions to a mask template. In our work, we propose leveraging contrastive models and a crowdsourced vocabulary to assign tags and attributes to images, which, when combined with a frozen LLM, can solve various vision and language tasks, such as image captioning. Section 2.3.2 Vision and Language Tasks. In this section, we're discussing how large language models, LLMs, are applied to vision and language, VNL, tasks. This application is essentially broken down into two major categories. Firstly, we have multimodal pre-training. Here, visual and linguistic data are meshed together in diverse ways. For instance, some methods choose to only tweak the visual decoder, producing outputs that are fed into a stationary LLM. Techniques like Flamingo, on the other hand, introduce additional layers that allow the two types of data to interact more closely. Other examples, like Blip2 and Mini GPT-4, simplify this process by shrinking extra layers and incorporating streamlined modules, while keeping the vision encoder static. The common thread across all these methods, however, is the complex alignment of visual and linguistic data, which demands considerable computational power and a substantial amount of training data. This makes it difficult to harness the full potential of cutting-edge LLMs. Moreover, these techniques can sometimes impair the reasoning capabilities that LLMs are famous for. The second category is language-driven modular alignment. This approach interlinks LLMs with different modules to bridge the gap between visual and linguistic data. Simultaneous research utilizes ready-to-use LLMs to tackle purely visual question answering tasks, such as VQA 2.0 and OKVQA. In contrast, Lens expands the capabilities of LLMs to also address object recognition tasks, without needing any question-guided information extraction. A different research piece, PromptCap, designs a question-aware captioning model, trained with synthetic examples using GPT-3, to tackle VQA tasks. Meanwhile, Lens employs vision modules, eliminating the need for any additional pre-training stage. Viper GPT also uses black box LLMs like Instruct GPT and Codex to achieve impressive results on various VQA benchmarks, but it leans heavily on BLIP2, which requires extra rounds of multimodal pre-training. It's important to note, though, that all these methods follow a top-down strategy, where attention mechanisms are directed by non-visual or task-specific contexts. However, our proposed method deviates from these traditional methods, employing a bottom-up approach. This strategy doesn't require any question-guided information extraction, which is often a more complicated task. Despite this, Lens manages to achieve commendable results that are on par with question-aware models. Section Summary. Vision and language tasks can be approached in two ways: multimodal pre-training and language-driven modular alignment. Multimodal pre-training aligns vision and language modalities through various methods, but it requires significant computing resources and can hinder reasoning abilities. Language-driven modular alignment couples LLMs with different modules to align visual and language modalities, and our proposed bottom-up approach achieves notable results without question-guided information extraction. Section 3 Method. In Section 3, we introduce a groundbreaking framework named Lens, which aims to augment the abilities of existing language models by enabling them to handle visual as well as visual and language tasks, on top of their inherent natural language understanding capabilities. Differentiating itself from the current methodologies, Lens introduces a unified platform that simplifies the process of a language model's reasoning module, working on text data sourced from a collection of individual and comprehensive vision modules. The crucial advantage of Lens is that it eradicates the need for high computational resources that are typically required to sync the visual domain with the text domain via extra joint pre-training on multimodal data, an essential step in previous work for handling visual and language tasks. In simpler terms, given an image I, we employ the vision modules to draw out every possible textual detail T that accurately describes the image, including objects, attributes, and captions, without constraining it to specific task directives. Following this, an existing language model can process the broad prompts T combined with task-specific prompts, and carry out tasks like object recognition or visual reasoning. In this section, we elaborate on the key features of the vision modules, explain the primary elements of Lens, and then delve into the design of the prompts. 3.1 Visual vocabularies. In the Lens framework, visual vocabularies play a pivotal role as a medium to transform an image into textual data that can then be processed by a pre-existing language model. We formulate vocabularies for usual objects and attributes. Tags. To assemble a varied and exhaustive tag vocabulary for a model's image tagging, we gather tags from numerous sources. These sources encompass multiple image classification datasets, object detection, and semantic segmentation datasets, as well as the visual genome dataset. Attributes. Pursuing the approach presented in our methodology, we use a robust language model, GPT-3, to generate descriptions of the visual attributes that distinguish each object category within our object vocabulary. Section Summary. The section describes a framework called Lens that enhances the capabilities of language models by enabling them to handle both vision and language tasks. Lens eliminates the need for joint pre-training on multimodal data and aligning the visual and text domains, allowing a frozen language model to process textual information extracted from vision modules and perform object recognition or visual reasoning tasks. The section also discusses the creation of visual vocabularies for objects and attributes to convert images into textual information. Section 3.2 Lens components. The system we're discussing, named Lens, is made up of 4 main components. 3 of these are related to visual processing, and 1 is focused on reasoning tasks. Let's break down each modules. Role. The tag module is our initial point of interaction with an image. It assigns relevant tags to the image, essentially identifying the main elements within it. We use a vision encoder, specifically CLIP, to select the most appropriate tags for the image. We've standardized our process by using a common prompt, a photo of class name, for object tagging. This ensures our system remains flexible across different domains without needing manual adjustments or ensemble prompt tuning. The objects we can tag come from the vocabulary we built in a previous section of our work. The attributes module comes next. Its job is to determine and assign relevant attributes to the objects in the image. To do this, we use the same vision encoder, CLIP, but with task-specific prompts. The encoder then classifies the objects based on an attribute vocabulary we previously generated. The intensive captioner is our third visual module. Here, we employ an image captioning model named BLIP, which we use with stochastic top-K sampling to produce multiple captions for each image. This method enables us to capture various elements and perspectives within the image's visual content. These captions are then forwarded to our reasoning module without alterations. The reasoning module is our final component, and it's different from the others. It doesn't deal with vision but with reasoning tasks. We use a pre-trained language model, kept in a frozen state, that can create answers based on textual descriptions supplied by the visual modules, coupled with task-specific instructions. The advantage of Lens is that it can easily pair with any black box language model, enhancing these models with vision capabilities and thus speeding up the overall process. Now, about the prompt design. We use the text information provided by the vision modules to construct full prompts for the language model. For the tag module, we format it as tags, top K tags. For the attributes module, it is attributes, top K attributes. And for the intensive captioning module, we have captions, top N captions. For a specific task related to identifying hateful memes, we add an OCR prompt formatted as OCR. This is an image with written meme text on it. Finally, we incorporate a question prompt followed by a space for a short answer. You can see this prompt structure in action in our demo. Section Summary. The lens system consists of 3 vision modules, tag module, attributes module, intensive captioner, and 1 reasoning module. The vision modules use clip to identify tags, attributes, and generate diverse captions for an image. The reasoning module, based on a frozen LLM, generates answers using the textual descriptions from the vision modules and task-specific instructions. The prompts for the LLM are constructed by combining the outputs of the vision modules and appending a specific question prompt. Section 4 Experiments. Section 4 Experiments. In this section, we delve into a comprehensive series of experiments and analyses to demonstrate the effectiveness of our model, Lens. Our first task is to pit Lens against other top-tier models in the field of object recognition. Next, we put Lens to the test in tasks related to vision and language reasoning, contrasting it with multimodal foundation models. In addition, we engage in ablation studies where we scrutinize key design choices like the components and patterns of prompts for each task. Subsection 4.1 Datasets. We use 9 recognized datasets to test our model's object recognition capabilities. Our aim is to highlight how our frozen language learning models, LLMs, can integrate contextual learning by evaluating Lens in 0-shot, 1-shot, and 3-shot settings. For vision and language reasoning tasks, we concentrate on 0-shot benchmarks because we observed no enhancements when we tested Lens in few-shot settings. We evaluate our approach using the test dev split of the VQA 2.0 dataset, the OK VQA dataset test set, the dev and test scene sets of the hateful memes dataset, and the test set of rendered SST2. If you need an in-depth understanding of each task, including details like dataset sizes, the number of classes, and the precise evaluation metrics used, please refer to the table in the supplementary material. Subsection 4.2 Implementation details. In both the tags and attributes modules, we employed OpenClip H142 and Clip L143 as our go-to vision encoders. For the intensive captioning module, we used a model called Blip Large 4, which was fine-tuned on a dataset named Coco. Here, we used a process known as top K sampling, where K denotes the desired number of captions, allowing us to generate up to a maximum of 50 captions per image. The Flan T5 models serve as our default family of frozen LLMs. To generate answers that align with the evaluation tasks, we used a strategy called beam search with 5 beams. We also applied a length penalty of -1 to encourage concise answers. These experiments were carried out using 8 NVIDIA A100 40GB GPUs. To achieve optimal performance with Lens, we performed task-specific optimizations. In the context of object recognition, we utilized the tag module, operating on classes relevant to each dataset. Moreover, we utilized the attribute module, which leverages an attribute vocabulary. Based on preliminary results, we decided to bypass the intensive captioning modules. In tasks related to vision and question answering, VQA, we exclusively used the intensive captioning module, as we found that tags and attributes did not offer any significant improvement. However, when working with the hateful memes and rendered SST2 datasets, we integrated the tag, attributes, and captioning modules, generating a single caption using beam search with a width of 5. Section Summary. In this section, the authors conduct experiments to demonstrate the effectiveness of their model, Lens. They compare Lens with other state-of-the-art models in object recognition and evaluate its performance in vision and language reasoning tasks. They also perform ablation studies to analyze the impact of different design choices. The experiments are conducted on various datasets, including benchmark datasets for object recognition and 0-shot benchmarks for vision and language reasoning. The authors provide implementation details, including the vision encoders and frozen LLM models used, as well as the optimizations made for each task. Section 4.3 Results. Section 4.3 Results. Our work centers around evaluating Lens in the realms of visual and combined visual and language tasks. Focusing on visual tasks first, we conducted tests across 8 benchmarks, comparing the results with top-tier models for object recognition in 0 and few-shot settings. Within the realm of visual and language tasks, we studied 4 key tasks that are representative of visual question answering. Here, we drew comparisons with cutting-edge models that employ a static LLM, language learning model, needing additional pre-training phases, and extensive datasets of coupled data for aligning the visual and language aspects. Interestingly, in these tasks, we found that in-context learning did not enhance the results in our zero-shot experiments. Let's look more closely at object recognition. We discovered that the lens model, which combines the VIT-H14 as the visual backbone and FLAN T5XXL as the static LLM, outperforms the same size clip model, which uses a standard prompt, by an average of plus 0.7%. An interesting insight from our experiments is that in object recognition tasks, the size of the static LLM doesn't seem to directly impact classification performance. However, we noticed a trend between the size of the tagger structure, VIT backbone, and performance. By examining average visual performance across all datasets, excluding ImageNet due to its large size, we found that increased shots improve performance regardless of the combination of visual backbone and frozen LLM used. Moreover, we reaffirmed the lack of a direct link between an improved static LLM and performance, yet noticed that a superior visual backbone enhances average visual performance. Turning to vision and language, we compared the performance of Lens against other systems. Lens proved highly competitive, even when stacked against more complex and larger systems like Flamingo, Blip2, and Cosmos. Specifically, our lens model with FLAN T5XXL achieved superior results on the VQA 2.0, outperforming Flamingo 9B and Cosmos 1 by 11% and 15% respectively. In addition, Lens surpassed the most powerful version of Flamingo by 6 points. We also found that our intensive captioning module, which uses a VIT-L vision encoder, matches the performance of the largest Blip2 structure that employs VIT-G as its vision encoder. Our best lens model outshone multiple versions of Flamingo on the hateful memes test and outperformed Cosmos on the rendered SST2 benchmark. It's worth noting that our success on the rendered SST2, a benchmark where a strong language model is required to comprehend the sentiment of the text extracted from an image, is unsurprising. This test isn't just about connecting image features directly to text, it's also about interpreting the actual meaning of that text. However, on the OKVQA test, our model's performance fell short of matching Flamingo's. This may be due to Flamingo 80B's use of the 70B Chinchilla language model, which has a larger knowledge base than our best reasoning module. Section Summary. In our evaluation of Lens, we found that it outperforms state-of-the-art models in object recognition tasks, even when compared to models with larger language models. We also observed that the size of the visual backbone architecture has a direct impact on performance. In vision and language tasks, Lens demonstrated highly competitive performance compared to larger and more sophisticated systems, achieving superior results in tasks such as visual question answering and intensive captioning. However, our model's performance on OKVQA did not match that of Flamingo, potentially due to the larger knowledge base of Flamingo's language model. Section 4.4 Ablations on Lens Components. In Section 4.4, we delve into the disassembly of Lens's components and their individual influence on object recognition. Using FLAN T5XL and Clip H14, we conducted an examination into how each component of Lens performs in isolation and in combination. The findings of our exploration are documented in the provided table. The utilization of the tag module alone yielded a performance equivalent to that of Clip H14. The standalone usage of the attributes module, however, led to a notable dip in the performance levels. Yet, when we paired the attributes module with the tags, we saw a notable enhancement in Lens's performance, by 0.4%. The takeaway here is that Lens proves to be a sturdy foundation for object recognition tasks compared to using only one vision module, like Clip. For a more granular view of how Lens performs on each dataset, we recommend checking the table in the supplementary material. As for visual reasoning tasks, we tested our model, equipped with FLAN T5XXL, on the minimal split of the VQA 2.0 dataset. We noticed that augmenting the number of captions generated by our intensive captioning module resulted in a steady improvement in performance. Nevertheless, there is a limit to this benefit, as performance plateaus after a certain point. This suggests that the intensive captioning module can only enhance the interpretation of an image up to a certain extent. We also performed ablation studies on the Lens components using the development set of the Hateful Memes benchmark. Our findings indicated that the best results are achieved by combining global captioning, tags, and attributes modules. Interestingly, the tags and attributes modules contributed more to the overall performance improvement compared to the global captioning module, particularly when paired with OCR. Despite this, we stress the importance of all these components, as their collective usage ensures the highest level of performance. To exemplify Lens's reasoning abilities, we showcase some qualitative examples in Fig. that demonstrate Lens answering questions about intricate scenes and scenarios. Section Summary. In this section, the authors conducted ablation studies on the components of Lens, a model, for object recognition and visual reasoning tasks. They found that using only the tag module resulted in similar performance to CLIP H14, but using only the attributes module led to a drop in performance. However, when combined with tags, attributes significantly improved the performance of Lens. For visual reasoning, increasing the number of captions generated by the intensive captioning module improved performance up to a certain threshold. The combination of global captioning, tags, and attributes modules was essential for achieving high performance on the Hateful Memes benchmark.